The concept of entropy, a measure of disorder and randomness in a system, plays an important role in predicting the end of the world. According to the second law of thermodynamics, in closed systems entropy increases with time until it reaches a maximum. This basic principle of physics states that the universe can be viewed as a closed system moving toward a state of maximum entropy. This increase in entropy is often associated with the end of the world, leading to a phenomenon known as the triumph of entropy. In a world of high entropy, all energy distributions would be equal, and temperature differences would disappear. Homogeneity means that no work can be extracted from any part of the universe, since work depends on moving energy from areas of high concentration to low concentration. In such a state, all energy-consuming processes such as life, star shining, planet formation, or even black hole evaporation will cease. The universe will reach a state known as thermal equilibrium, where all points in space will have the same temperature and no more changes will occur. Visualizing a universe dominated by entropy evokes a picture of cosmic immobility and monotony. The bright space we see today, with its galaxies, stars, and planets, would be replaced by featureless space. Stars would run out of nuclear fuel. Galaxies would no longer form, and black holes, the last bastions of gravitational order, would vaporize as a result of Hawking radiation. All that would remain would be a dilute soup of particles and radiation scattered over ever-expanding space, with no gradients to drive motion or form structures. As the universe moves inexorably toward its finale, the last black holes stand as monuments to earlier and more turbulent eras of the cosmos. These gravitational giants, remnants of decayed stars and engines at the centers of galaxies, would undergo a slow but inevitable transformation that would have profound implications for the ultimate purpose of the universe. The key to understanding their fate lies in a process known as Hawking radiation, a theoretical prediction by physicist Stephen Hawking that black holes are not completely black, but emit radiation due to quantum effects near their event horizons. Hawking radiation results from the creation of particle-antiparticle pairs in the vacuum near the event horizon of a black hole. From time to time, one particle falls into the black hole and another flies out, causing the black hole to lose mass over time. For large black holes, this process is extremely slow. It takes many orders of magnitude longer than the current age of the universe to have a noticeable effect. However, as the universe ages and expands, these last black holes will become protagonists on the cosmic stage, gradually vaporizing their mass in the form of Hawking radiation. The evaporation of the last black holes marks an important milestone on the universe's path toward maximum entropy and thermal equilibrium. By emitting Hawking radiation, they not only lose mass, but also eject energy back into the universe. However, this energy will be distributed in the increasingly rarefied space, contributing to an overall cooling and erosion of the energy density in space. When the last black hole evaporates, a process that could take up to 10 near-flexible 100 years, a time frame beyond human comprehension, there will be no significant concentrations of mass and energy left in the universe capable of forming new celestial bodies or driving cosmic phenomena. The significance of the evaporation of the last black hole goes beyond their role as cosmic reference points. It symbolizes the transition of the universe to a state in which no large-scale structures exist, and all that remains are low-energy photons, electrons, neutrinos, and possibly dark matter particles scattered throughout an ever-expanding space. This state represents the ultimate embodiment of entropy's triumph, a universe in which all available energy is used up and no work can be done. In the distant future, as the universe ages and evolves toward a state of maximum entropy, conditions for life as we know it will become increasingly difficult. Theoretical assumptions about survival in a degenerate universe, where stars have gone out and black holes have evaporated, paint a picture of extreme adaptation and ingenuity. If any forms of life or consciousness can survive in this distant future, they will have to adapt to the harsh conditions of a dying universe in ways that push the limits of our current understanding of biology, physics, and engineering. In such a universe, traditional sources of energy, such as sunlight or chemical reactions, would be scarce or non-existent. One possible survival strategy involves utilizing the most fundamental and common sources of energy. For example, civilizations will be able to harness the Hawking radiation energy emitted by evaporating black holes, although this will require technological advances far beyond anything currently imaginable. Another speculative strategy might involve the direct conversion of mass to energy. As matter becomes increasingly dilute in an expanding universe, extracting useful energy from rare particles and radiation may be a way to sustain life. Advanced forms of matter manipulation or even energy extraction mechanisms at the quantum level that allow direct harnessing of the energy of subatomic particles could be utilized. Survival in a degenerate universe may also require radical changes in life forms themselves, perhaps through bioengineering or the development of post-biological life. Life could take the form of highly efficient, low-energy beings capable of functioning in an environment with minimal resources. These beings could be engineered to hibernate for long periods, awakening only when energy conditions are favorable, or to exist in a state of reduced metabolic activity, extending their lifespan to eons. Furthermore, given the isolation caused by the vast distances between the remaining energy sources, any surviving creatures should probably be highly autonomous, able to repair, reproduce, and evolve without outside interference. This could lead to forms of life or consciousness that are fundamentally different from anything we know, potentially based on entirely new substrates such as quantum computing structures that can operate at minimal energy levels. Communication and travel will present significant challenges in a degenerate universe, possibly forcing surviving beings to develop highly advanced forms of information storage and transmission capable of surviving the long cosmic night. Information may become the primary currency of exchange, and the preservation and transfer of knowledge will be vital to the preservation of any form of society. In a universe heading towards its ultimate fate, be it heat death, the Big Rip, or some other scenario, our understanding of time and causality, the fundamental concepts underlying our perception of reality, may be profoundly tested and altered. The arrow of time, a metaphorical expression used to describe the one-way direction or asymmetry of time, is closely related to the second law of thermodynamics, which states that entropy in a closed system does not decrease with time. As the universe evolves toward a state of maximum entropy, nuances may emerge in the very fabric of time and causality that are not accounted for in our current understanding. In the distant future, as the universe approaches a state of thermal equilibrium in a heat-death scenario, the absence of discernible events may make it appear from some vantage point that the flow of time has stopped. Without changes in the energy states that mark the passage of time, beings in such a universe would not be able to experience time in any meaningful way. This raises philosophical questions about the nature of time. Is it a fundamental part of the universe, or is this an emergent property, dependent on the existence of change and causality? The concept of causality, the relationship between cause and effect, may also be reconsidered in a universe nearing its end. Quantum mechanics is already challenging classical notions of causality with phenomena such as entanglement, where particles can affect each other instantaneously regardless of distance, seemingly contradicting the conventional flow of time. As we explore the fate of the universe, we may find that the fabric of space-time and the rules governing causality on cosmological scales create new paradoxes and possibilities that are beyond our current quantum mechanical understanding. Moreover, if speculative theories such as the cyclic model of the universe, in which the universe undergoes an endless series of expansions and contractions, or the existence of a multiverse, prove true, our perception of time as a linear progression from a singular beginning to a singular end may be too simplistic. In such scenarios, time may be better conceptualized as a more complex, perhaps even multidimensional landscape, where causality operates in ways that are not immediately intuitive to our current thinking. These considerations suggest that, as the universe evolves, the beings living in it, if only they can survive the harsh conditions of the distant future, may develop an entirely new framework for understanding and perceiving time and causality. These frameworks may account for the altered physical conditions of a maximally entropic universe, or incorporate insights from quantum mechanics and theoretical physics that challenge our current paradigms. Quantum fluctuations, temporary energy changes occurring in a seemingly empty vacuum, represent the cornerstone of quantum mechanics, revealing the inherent unpredictability and activity of the quantum vacuum. In the context of a dead universe, a space near or reaching maximum entropy, devoid of stars and galaxies and approaching absolute cold, such fluctuations could still occur. Intriguingly, some theoretical physicists suggest that, under the right conditions, quantum fluctuations can give rise to new universes, suggesting that cosmic events may be cyclical. In a universe that has reached its final state, where matter is dilute and energy is evenly distributed, the fabric of space-time can still experience quantum fluctuations. In principle, these fluctuations could lead to the formation of low-energy virtual particles, a phenomenon observed in the laboratory. Extending this concept, it suggests that under extremely rare and specific conditions, a quantum fluctuation can create a localized concentration of energy dense enough to cause a new Big Bang, generating a new universe within the old one. This concept is related to the idea of a multiverse, where our universe is just one of potentially many universes, each with its own physical laws and constants generated by the quantum foam of a larger multiverse. Such a process implies cyclicity, or at least a constant nature of cosmic events, where the death of one universe sets the stage for the birth of another. The implications of such a scenario are profound, challenging our understanding of time, causality, and the very nature of existence. If quantum fluctuations can indeed produce new universes, this suggests that the cosmos is eternally rejuvenated, with cycles of birth, evolution, and death followed by rebirth. This cyclic model contrasts with the linear progression from Big Bang to heat death traditionally represented in cosmology. Singularities inside black holes, points of infinite density, where the laws of physics as we know them break down, have long fascinated physicists and cosmologists. A tantalizing hypothesis suggests that these singularities may not simply mark the end of the journey of matter within our universe, but may also serve as seeds for the birth of new universes. This idea suggests a profound connection between the end of one cosmic epoch and the beginning of another, weaving a tapestry of universe creation that links the life cycle of black holes to the genesis of entirely new cosmoses. At the heart of a black hole, matter collapses into a point of infinite density and zero volume, forming what is known as a singularity. The conditions in these singularities go beyond our current understanding of physics, potentially involving the unification of general relativity theory, which describes gravity at cosmic scales, and quantum mechanics, which explains the behavior of particles at the smallest scales. Some theories, such as the concept of quantum gravity, attempt to describe these conditions by suggesting that the extreme gravity of a singularity can tear the very fabric of space-time. Theoretically, this rupture could create a bridge or wormhole to another region of space-time, giving birth to a new universe that expands in its own dimension, separate from our own. The new universe does not necessarily inherit the physical laws or constants of its parent universe, allowing for the creation of a variety of cosmoses with very different properties and complexity potential. The implications of black holes serving as seeds for new universes are profound. This challenges our understanding of causality, as the birth of a new universe from a black hole singularity means that the end of one world is inextricably linked to the beginning of another. This cyclic process could provide a mechanism for the emergence of a multiverse, where each black hole in our universe is capable of generating a new universe, leading to an ever-growing ensemble of universes. This concept changes our view of black holes from cosmic endpoints to gateways of cosmic rebirth. This suggests that within each black hole lies not just the end of certain paths in space-time, but the potential for entirely new beginnings. This view is consistent with the broader view of modern cosmology that the universe is a dynamic, constantly evolving entity, with processes at both the largest and smallest scales that contribute to the cosmic life cycle. If the multiverse theory is correct, and suggests the existence of multiple universes beyond our own, each with potentially different physical laws and constants, this opens up profound questions about the nature of consciousness, information, and their persistence beyond the life of a single universe. The intriguing possibility that consciousness or information could leave a dying universe and find refuge in another universe touches on the intersections of cosmology, quantum mechanics, and theories of mind and information. The basis of this speculative journey lies in understanding the mechanisms by which such a transference can occur. One theoretical path is related to quantum entanglement, a phenomenon where particles appear to be interconnected in such a way that the state of one of them, regardless of the distance between them, instantaneously affects the state of the other. Extending this concept, some theorists suggest that if every bit of information in our universe, including the states that constitute consciousness, could be entangled with particles in another universe, then, in principle, information transfer would not be associated with the death of the parent universe. Another potential mechanism is black hole singularities, which it is thought could serve as bridges or wormholes to other universes within the multiverse. If consciousness or information can be encoded in a form that survives a journey through such a singularity, it could be another avenue of escape from a universe facing doom. For consciousness itself to make such a leap, it is necessary to radically expand our understanding of consciousness as not just a product of brain activity, but as something that can exist independently of a biological substrate. This concept relies heavily on the realm of digital consciousness, or mind uploading, where human consciousness can be replicated on a non-biological platform capable of surviving the extreme conditions of inter-universe travel. However, each of these speculative paths faces serious scientific and philosophical obstacles. Quantum entanglement, although experimentally confirmed, currently makes it impossible to transmit information in a way that encompasses consciousness. Similarly, the nature of singularities and wormholes, and their ability to connect to other universes, remains purely theoretical and limited to our limited understanding of quantum gravity. The transference concept of consciousness suggests that it can be fully understood and reproduced outside of its biological context. And this claim raises profound questions about the nature of identity, selfhood, and the continuity of experience. As the universe approaches its ultimate fate, the principles of quantum mechanics and information preservation play a key role in shaping theories about the final moments of the universe and the possibility of its eventual rebirth. Information retention. A principle deeply embedded in quantum theory states that information, defined in the broadest sense encompassing all possible states of a system, cannot be destroyed even if it can be transformed. This principle has profound implications for the ultimate purpose of the universe and the concept of cyclicity or rebirth in cosmological models. At the center of these discussions is the concept of the black hole information paradox, which asks, what happens to information trapped in a black hole? Stephen Hawking's discovery that black holes emit radiation, Hawking radiation, and can eventually vaporize, has challenged the idea that information trapped in a black hole is lost forever. If black holes vaporize without leaving a trace, the question arises, where does information go? The principle of conservation of information suggests that it must be stored in some form, perhaps encoded in Hawking radiation itself. This debate has prompted more research into the nature of information at the quantum level and its implications for the universe. One theory suggests that at the end of the universe, all of its information could be encoded on a two-dimensional surface at its boundary, adhering to the holographic principle, which suggests that the entire volume of space can be described by the information at its boundary. This model could mean that, as the universe approaches its demise, all information about its history, structure, and content, perhaps even the rudiments of consciousness or life, could be preserved at this cosmic boundary. Theoretically, this stored information could be the basis for the rebirth or regeneration of the cosmos. If the universe is cyclic, as in models involving a series of big bangs and big compressions, then the information preserved at the end of one cosmic cycle could affect the initial conditions of the next. In such a scenario, the rebirth of the universe would not be tabula rasa, but would bear the imprints or echoes of its previous incarnation, guided by the fundamental laws of quantum mechanics and conservation of information. Progress in understanding quantum gravity, a theory that seeks to reconcile general relativity with quantum mechanics, may reveal the mechanisms by which the information preserved at the death of the universe affects the very fabric of space-time, potentially laying down the geometry and distribution of matter of the new universe. It is a symbol of a world where ends and beginnings connect, care for each other, and protect information. Human understanding and reflection on the end of life offers profound lessons about our place in the world and our approach to life issues, and provides us with a humbling and inspiring perspective. When we look at the vastness of the universe and think of its future, we are reminded of our smallest scale in space and time. Of course, this does not diminish our intelligence. Instead, it increases our appreciation of the complexity and beauty of the world and our ability to understand it. The cosmic perspective teaches us about the transience of existence, not only on a personal or species level, but on the scale of stars, galaxies, and the universe itself. It instills in us a sense of cosmic humility, recognizing that we are part of a much larger and ancient process far beyond our immediate concerns and lifespan. Realizing this can shift our existential questions from a human-centered narrative to a broader and more inclusive understanding of our place in the cosmic web of life and matter. Moreover, thinking about the end of the universe and the principles that govern it, such as entropy, the conservation of information, and the possibility of cyclic universes, causes us to think deeply about the nature of time, causality, and existence itself. These concepts expand the boundaries of human thinking, inviting us to consider that our universe may be one of many, that our existence is part of a larger cosmic cycle, and that the legacy of humanity and life as we know it may be encoded in the very fabric of the cosmos. Exploring these ideas also has practical implications for how we relate to our lives and stewardship of our planet. Recognizing the rarity and value of life in the context of the cosmos can inspire a deeper sense of responsibility to preserve and cherish the delicate conditions that allow life to thrive on Earth. This can motivate us to strive for a sustainable existence, to explore interstellar space, and to preserve knowledge, culture, and biodiversity for future generations. The realization of the ultimate end of the universe provides a powerful stimulus for human creativity, philosophical reflection, and the urgent need to find meaning in our existence. This profound realization that the cosmos itself is not eternal and unchanging, but subject to decay and transformation, touches the very core of our understanding of life, purpose, and the nature of existence. It forces us to face the finitude of everything we know and challenges us to find meaning and purpose within those boundaries. In terms of creativity, thinking about the demise of the universe has inspired countless works of art, literature, and music, as well as innovations in science and technology. Artists and thinkers have long addressed the themes of impermanence and the end of time, using these concepts as a backdrop against which the drama of life unfolds. The vastness and mystery of the cosmos, coupled with its ultimate end, serves as a muse for exploring the depths of human emotion, fortitude, and boundless capacity for imagination. This realization motivates scientists and innovators to go beyond our current capabilities, to explore the cosmos, to comprehend the fundamental laws of nature, and to contemplate the possibility that we may go beyond our earthly origins and perhaps even the lifespan of our universe. Philosophically, the end of the universe forces us to reconsider the existential questions and values that guide our lives. It prompts reflection on the nature of values, ethics, and our responsibilities to ourselves, to each other, and to the continuity of consciousness and culture. The finitude of the cosmos can lead to a deeper appreciation of the moment, a deeper investment in the legacy we leave behind, and a deeper understanding of the interconnectedness of all things. Such a perspective fosters a philosophy of stewardship that emphasizes the nurturing of life, knowledge, and beauty, despite, or perhaps because of, their transitory nature. The need to find meaning in our existence is perhaps the most direct consequence of thinking about the end of the universe. Faced with the ultimate impermanence of all things, people begin to seek purpose in their actions and relationships, to create and share the beautiful, and to make a lasting impact on the world and those around them. This awareness can lead us to move from seeking external validation to cultivating inner wealth, from accumulating material goods to enriching the world with contributions that can endure through time. In envisioning the preservation of knowledge through the ages, humanity stands on the threshold of an endeavor that strikes the imagination to the extreme. This mission to pass on the legacy of our knowledge and existence to possible future civilizations or minds requires innovative methods and messages that can withstand the ravages of time and the uncertainty of cosmic events. The challenge is not only to preserve information, but also to make it understandable to people with potentially very different perceptions, languages, and technological capabilities. One approach to this grand challenge is to create lasting time capsules or monuments that are designed to last for millions or even billions of years. These could be plaques or sculptures made of materials resistant to erosion, corrosion, and cosmic radiation, such as platinum or silicon carbide. One example is the Voyager Golden Record, which is currently traversing space aboard the Voyager spacecraft, and contains sounds, music, and images selected to represent the diversity of life and culture on Earth. Another method involves encoding knowledge in the structure of DNA, taking advantage of its longevity and compactness as a storage medium. Scientists have already made advances in storing digital data in DNA, a technique that could be extended to archiving vast amounts of information about human history, culture, science, and technology. DNA can be encapsulated and placed in many places on Earth and beyond in the hope that future beings, whether descendants of humanity or extraterrestrial intelligent beings, will be able to decipher it. The messages we choose to preserve should be composed with universal principles and concepts in mind, aiming at a level of communication that transcends human language and cultural sensitivities. These could be mathematical sequences, physical constants, or simple pictograms depicting fundamental aspects of human anatomy, the location of the Earth relative to known celestial objects, and basic concepts of chemistry and biology. An example of this approach is the Arecibo message sent into space in 1974. It used binary code to transmit basic information about humanity and the solar system. In addition to physical methods, humanity might consider more speculative strategies, such as attempting to transmit information through time using quantum entanglement or other phenomena that lie beyond our understanding of physics. Although such ideas belong to the realm of science fiction, they reflect the breadth of creative thinking aimed at solving the problem of intertemporal communication. In addition, a method of preserving knowledge can be the development of a culture of preservation and continuity within human civilization itself. This could include the continual updating and preservation of knowledge repositories, specialized institutes, or digital archives designed to survive global catastrophes and be accessible to future generations. Such repositories would hold not only information, but also instructions for interpreting the data, perhaps the keys to understanding human languages and technology. As humanity becomes more aware of the universe and our place in it, the realization of our ultimate destiny brings to the fore a number of ethical considerations of cosmic proportions. These considerations challenge us to think about how we interact with the cosmos, what responsibility we have to future generations, and how we should interact with potential extraterrestrial life. Our actions, motivated by the realization of the immensity of the universe and its ultimate demise, have implications that go far beyond our immediate concerns and go to the very core of our heritage and stewardship of the cosmic environment. First, ethical engagement with the universe requires a deep respect for the cosmos as the broader context of our existence. This respect is manifested in the desire to preserve outer space and to refrain from activities that could have a negative impact on the celestial environment. As we venture into space, the principles of non-pollution and preservation of celestial bodies in their natural state become paramount. These principles not only preserve the scientific integrity of these environments for future exploration, but also consider the intrinsic value of the cosmos beyond human utility. Second, our understanding of the fate of the universe increases our responsibility to future generations. This responsibility entails ensuring that future generations inherit a wealth of knowledge and a culture of curiosity and exploration. It also involves developing and preserving technologies and information that can help humanity meet the challenges of a changing universe, including the search for new habitats beyond Earth. The need to invest in long-term sustainable life and interstellar exploration is a testament to our commitment to the continued existence of humanity and Earth. Furthermore, the prospect of encountering extraterrestrial life raises complex ethical dilemmas concerning communication, coexistence, and knowledge sharing. The principles of mutual respect, non-interference, and the peaceful exchange of resources and information must underpin our interactions. Recognizing the rights and autonomy of other living beings and interacting with them in ways that promote mutual understanding and respect represents our commitment to ethical behavior not only at home, but also in space.